What's going on, my chemistry students? I'm really excited for this class, and let's get this party started. I really wanted you to go through the stoichiometry lab that I posted last week, Wednesday. It's due on Wednesday, so I'm not really like getting too like upset about you folks for not doing the lab because you still have time to do it. But knowing or going through the lab will really help you out in this chapter. So in this chapter, we're going to cover a lot of the stuff that I introduced to you in a very difficult but creative way on the lab where you get to make s'mores and everything. Counting by weighing, the molar mass, all of that kind of stuff. Even this concept of limiting reactants is covered in this lab, and I'm really excited about it. So what I'm really excited about doing is not necessarily this lab, like, oh, this lab that I created, oh, Mr. Dalday, yeah, he's so great, and he creates all of these great things. No. What I'm really excited about is today's class and also Wednesday's class, because I get to finally explain to you what I introduced to you back when we did the lab. Is that cool? Does that make sense? All right, so let's talk about this stuff. One of the things we ended up doing is we found in chemistry that we count by weighing something. And for example, I like their example that they use when they talk about like jelly beans, and they said if you had to measure out like 3,000 jelly beans or 1,000 jelly beans, you wouldn't actually sit there and count 1,000 jelly beans. That would be dumb. What I would do if I were you is I would count out maybe 10 jelly beans. And if I count out 10 jelly beans, then I can weigh that. And then I just say, all right, well, then I get my scale and I poured the jelly beans until it equals to 10 times the weight of 1,000 or of 10 jelly beans, and that gives you 1,000 jelly beans. So for example, if 10 jelly beans weighed like 50 grams, then when I want to count out 1,000 jelly beans, I would just basically pour jelly beans on my scale until I reached 500 grams. Or not 500, 5,000. Because 10 times 100 is 1,000. Sorry, screwed that up. Does that make sense? So I would weigh out 5,000 grams of jelly beans, which comes out to be like, I think like 10.5 pounds. Something ridiculous like that. It's a funny story, really, and I have all these funny stories, but I'll tell it to you really quickly. I went to Japan once because I played inside of a rock band. It was actually a ska band, and we toured in Japan. And one of the things we did was I would cook stew for like one of the days I was in charge of cooking. So I cooked stew, and I went to I usually go out and get like 5 pounds of beef for my stew, but I went and I went to the store and I said, hey, I'd like five pounds of the beef, and I guess they thought that I said 5 kilograms, so I ended up walking home with like 10. Actually, I think it was like I ended up cooking more. I ended up walking home with like 20 pounds of meat, and I was like, whoa, because Japan uses the kilogram system. I didn't even realize that. All right, anyway. Then I stopped becoming a musician, became a nerd instead, studied physics, and now I'm a teacher. Yes, I made the right decisions. Actually, I think I did. I really like teaching math and science. But anyway. Yeah, we ended up making like stew and spaghetti and all of this kind of stuff for like the next week. I made like beef stroganoff. All right. So, you understand this? Does this concept sit well with you about like I'm going to count out something, but instead of counting it, I'm just going to measure it? Now, granted, if you want to get super accurate, then you should probably have somebody sit down and count out 1,000 jelly beans. But if you wanted to get like a ballpark figure, a really accurate ballpark figure, you could measure it. and just get a good scale, and you'll be happy. I mean, you might have 1,001 jelly beans, or you might have 999 jelly beans that you'd be giving the person, but I'm sure that they won't make a big deal out of it. And if they come back and say, look, you only gave me 998 jelly beans, I bought 1,000, then I would reach in my jelly bean thing and give them to and say, get out of here. All right. No, I would be much nicer than that. Yeah, counting jelly beans would be so long. Well, here's the thing. What happens if we're talking about like wanting to count out molecules in or atoms of an element? We're dealing with really, right, first of all, well, I'm getting to that grouping part in just a second, but first of all, we don't really want to deal with actually counting them. First of all, you can't even count them. I mean, we have microscopes now that you can actually count them, but it wouldn't be as easy as counting jelly beans. It'd be counting little dots on a electron microscope or whatever. And it'd be a real pain in the butt, especially if you wanted to count out like a reasonable amount of stuff. You would be there counting all day, probably not even all day, probably for the rest of your life and the rest of your grandkids' life, whatever. But because they're really small. But before I get to that, let's talk about this concept of atomic mass. Now, we were able to find that different elements have different masses. And we know that because there's different numbers of protons and neutrons in the different elements, right? And we talked about how a different number of protons makes a different element completely, whereas a different number of neutrons makes a slightly heavier or slightly lighter version of that same element. And we can analyze them using this mass spectrometer. Basically, you have a sample of maybe, let's say, carbon-13. And this would be carbon that has, well, where is my, let's look at the periodic table real quick. Carbon is 6 right here. Do you see it? Carbon 6. So it has 6 protons, and in carbon 12's case, it has 6 protons and 6 neutrons. Hence making carbon 12, because 6 plus 6 is 12. Whereas in carbon 13's case, it has 6 protons. Oh, I'm sorry. I looked it up on the wrong computer. No, I didn't. I accidentally looked it up on the computer, on a different computer. Anyway, if you look up carbon, you'll see that there's like a 6 and a carbon right here. Actually, fine. I'll look it up on the right computer. Here we go. Let's look up the periodic table. Here we go. Periodic table. Periodic table. Don't reload. Don't freak out. I'm just getting a periodic table. There we go. You look at carbon, it's got 6 protons right here. That 6 protons kind of means that we're dealing with, we're dealing with 6 protons, and it has, it must have 6 neutrons as well, because we're dealing with carbon 12. Whereas if we have carbon 13, then we have 6 protons and 7 neutrons that we're dealing with, making it a heavier version of carbon. And those are called isotopes. We've covered that already, right? So check this out. You have your sample of carbon-13 versus you have your sample of carbon-12. And it's just a little thing of stuff. Let's see. Let's make this guy a fat guy riding a bike. And we'll make this person a skinny guy. So we'll make this person a little tummy right there. And we'll make this person a skinny person riding a bike. Got it? And we'll do this. We'll have a really strong wind going this way. Actually, you know what? Let me make it going the other way. So I have a really strong wind going this way. All right. Now, when they're both riding their bike, they're both going to ride it as straight as they possibly can. But here's the problem. The really strong wind is going to blow the skinny guy, and the really strong wind is also going to blow the really fat guy equally as much. But the path of the really fat guy is probably not going to deviate very much, whereas the path of the really skinny guy is going to go like this. Does that make sense to you? So, what we do in mass spectroscopy is we have this thing where it's like a magnetic field, and we shoot our magnetic field, and it changes the course of these things. And depending on how much deflection occurs or how far away from the original part, we can kind of tell the difference between the masses of these different ions. And so that's how we're able to measure the masses at these such small levels. Are we cool? Does that make sense to you? Okay. All right, cool. So, mass spectroscopy explained through a fat guy and little guy riding bike. All right. So we came up with this unit called the atomic mass unit. And it's the mass of one proton or neutron. They're about the same. They're the same enough to be able to say that they're the same. And then so we said, all right, well, let's see. A sample, let's do this example. A sample of natural copper is vaporized and injected into a mass spectrometer, as results showed in figure 3.3. I think that's the one I just showed you. Use the data to compute the average mass of natural copper. The mass values for copper is 63, 65, are 62.93 and 64.93 respectively. Okay, so what do we know? To calculate the average mass of natural copper, you have, you know that copper 63, Cu 63 is equal to 62.93 atomic mass units. And copper 65 is equal to 64.93 atomic mass units. As shown by the graph. All right. Oh, I see. They want us to take a look at this figure. Okay, all right. So they're saying that relative number of amounts. So apparently 69.09% of copper found in the world is copper 63, and only 30.91% of copper in the world is copper 65. So what we got to do is we have to figure out what the average is. But it's kind of like one of those weighted average questions. So what we're doing is we're saying, all right, if I have 100 atoms total, then 69.09 of those atoms will weigh 62.93 units per atom. Does that make sense? And then 30.91 atoms will weigh this one, 64.93 units per atom. And then I divide that whole thing by 100 because I'm dealing with out of, like I take the two amounts and I add them up together and I divide by the number of things I added. So I divide the whole thing by 100, and so my answer will be 63.55. So this will be the atomic mass unit of the copper that I'm dealing with, of the copper that I would find in the world. Now, for example, what I mean is like, if we look at the periodic table that I had, and we look at carbon, carbon 12 is the standard that we use in chemistry. But if you look at the atomic mass unit of carbon, it says 12.01. And my question is, what the heck is up with that? Why is carbon 12 not exactly 12 for the atomic mass unit? Does that make sense? And it's because there's isotopes that exist like carbon 13, and that offsets this average number so that it's not your average mass isn't exactly 12 for carbon, and for copper apparently it's not exactly 63, or it's not 60. Let's see, copper is over here. 29 times 2, it's not 68. Apparently it's much lighter. All right, Bradley, what is a mole? Let's move on to that. So check this out. The mole. All right. When you're dealing with counting eggs, okay? When you're dealing with counting eggs, here's the problem is a lot of times we're dealing with like large numbers, like 48. And so instead of saying 48, we would just say, oh, grab 4 dozen, because for some reason, dozen is associated with eggs very often. And the word dozen, immediately when I say the word dozen in your head, it immediately makes you think, oh, hey, that means a dozen. Yeah, it means 12 of something. Because I don't need a dozen eggs. I could have a dozen people. I could have a dozen pimples on my face. I could have a dozen fingers. I don't know many people who have a dozen fingers, but I'm just saying. You could have a dozen of, if you say the word dozen, it means 12 of whatever you're dealing with. There's this dude who came by. Actually, the mole wasn't created by Avogadro, but Avogadro made a lot of advances in science, and so they named it in his honor. But when we're talking about counting molecules, we need a bigger grouping system. Because you can imagine that if I have like a small sample of something, like a little tray of copper, and I ask you, how many molecules am I dealing with? You wouldn't tell me the answer in dozens. Yeah. Anastasios I just made up as my own unit, and it means 4. So it would be I have 3 Anastasios of pimples on my face, which is the same as 12. Yeah, you're right. The problem is you wouldn't even use Anastasios as a unit of measure or as a grouping of measuring things when you're talking about the molecules inside of this tray of copper or aluminum or iron or mercury or sulfur or iodine. Therein lies the problem, because the number is so incredibly large of molecules that we're dealing with. So what we did was we said, all right, we are going to make up another grouping number called a mole. Actually, M-O-L-E. And no, it's not the crazy, ugly looking creature. But what it is it's equal to a grouping number, like instead of a dozen, I'm going to call it 6. Actually, it's not exactly 6. It's 6.022 times 10 to the 23rd power. So really, if I were to write it out, it would be 6022 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. It's that big. I don't even know how to describe what that number is. Like, I couldn't tell you million, trillion, billion, alien, gazillion, but it's uku plenty. Although this concept isn't really that bad when you think about the fact that we're talking about molecules. So this grouping would kind of be reasonable. Now, where did we get this number from? Does it feel like this number came out of nowhere? And I'll be honest with you, I don't really know the history behind it, but I do know that if you take 12 grams of carbon-12, pure carbon-12, you will have exactly Avogadro's number of molecules that you're dealing with. So they said, let's take carbon-12, and since it's a pretty stable, commonly found element, and if you have 12 grams of this stuff, that is equal to 1 mole of this, it will equal to 1 mole of molecules. So much bigger than 12. And the units on moles is basically, it's this many things per mole. How did they test that? I'll be honest with you, I don't know. I guess I should have read it a little bit closer. All right. So, check this out. If I have let's do this example, all right? If I have 6 americium atoms, so let's look up what americium is. I think it's Am. It's way down here. Obviously, it was discovered by France. No, I'm kidding. It's discovered by America. All right. So see this number right here? It's hard to see. Yeah, it's the metal of the free. All right. This number right here, 243. Okay. 95 tells you how many protons in it this is. This tells you how many grams per mole we're dealing with. So if I had 1 mole of americium, it would weigh 243 grams exactly. Whereas if I had 1 mole of carbon, on average, it would weigh 12.01 grams. If I had 1 mole of oxygen, it would weigh 16 grams. This kind of goes back to that part of the lab, and this is the part that everyone really got upset at me about, when I gave you folks things in measurements of Anastasios. I said a group of 4 of this will weigh this much grams. This is kind of what I was getting at when I did something like that. Now you folks are like, oh, I see why you put us through so much crazy pain. It's because I was telling you this number, but instead of saying a group of Anastasio, like a 4, I'm telling you a group of moles. That's how many, I'm gathering 1 mole of nitrogen molecules, and it weighs 14.01 grams. So, anyway, moving on. If we have 6 atoms of americium, all right, then how much does it weigh? All right, so I know I don't like the way they went about this. I'm gonna, whoa, what just happened? No. I don't like the way they went about this. Let's see if I can get to the same answer using a different approach. If I have 6 atoms of this stuff, I guess the first question I would ask is, how many moles is that? So I would divide this by 6.022 times 10 to the 23rd atoms for every 1 mole. Does that make sense to you? I'm basically using this as a conversion factor. All right. So this tells me, because the atoms cancel, this tells me how many moles of this stuff I have. So I multiply them? No, I actually divide them because the 6.022 times 10 to the 23rd power is in the denominator. Then I know from the periodic table that 1 mole of this stuff, of americium, is 243 grams. Does that make sense? Where did I get the 243 grams per mole, you ask? Well, I looked up on the periodic table, and I looked for americium, which is down here, and that has 243 grams per mole. That's what that number on the bottom represents. So then you just use your calculator, and let's see. Someone do the calculator for me. What is 6 times 243 divided by 6.022? I'm guessing it's like 230 something. Use your calculator. That's the number off the top of my head. I'm not very good at calculating things in my head, though. I'm guessing it's like 200. No, 230. Come on, what's 6 times 243 divided by 6.022? 242. Oh, okay. Well, all right. 242 times 10 to the negative 23 grams. Do you understand why I did times 10 to the negative 23? Because this times 10 to the 23 over here is in the denominator. So I dealt with just the numbers. Number. And then I slapped on the scientific notation part, which is here's times 10 to the 23 in the denominator. So if I move it up to the numerator, it's times 10 to the negative 23. Now does it make sense? And technically this is not in scientific notation. This is, I would move the decimal place 23 times to the left this way. So if I put the decimal place over here, I would only have to move the decimal place 21 times to the left. Now this is in scientific notation. I'm curious to know if I got the same answer as them. Let's check. 2.42 times 10 to the negative 21 grams. Good, that's the answer I got. Does this make sense to you? Which I would assume, obviously 2.42 times 10 to the negative 21 grams is extremely small. Nothing you could probably weigh out on a scale. And if you could weigh it out, you must be a drug dealer, and I'm going to call the cops on you because no one needs a scale that sensitive. In fact, I don't even think drug dealers have scales that sensitive. There are labs maybe that have scales that sensitive. I don't even think that there are. I don't know. But what I'm saying is, obviously it would be small because we're talking about 6 atoms of something. We're not talking about a huge number of atoms of something. In fact, if you asked me to get you 6 atoms of americium, I would probably get you like 1 gram of the stuff and then, say, well, there's at least 6 there. Well, maybe that would be a good question to ask. Actually, let's go backwards. Let's do that. Let's do exactly what I said, except let's use aluminum this time. All right? Let's say we have 10 grams of pure aluminium, also known as aluminum, but in England they call it aluminium. Crazy English. We have 10 grams exactly of this stuff. How many molecules, how many atoms of aluminum makes up 10 grams of this stuff? Okay, so first thing I would do is I would look up the molar mass for aluminum. 26 point, I can't even see that. Can I click on a bigger periodic table? Oh, Yahoo. You're such a Yahoo. What does it say? Let me just view the image. Obviously, I'm not a fan of Yahoo. Google. Yes, please take me there, Google. I'm used to you. Periodic table. Images. Here we go. View image. Let's get close on it. Zoom in. All right. 26.98. Let's just leave it at that. 26.98 grams per mole. So if I had 1 mole of this stuff, it would weigh 26.98 grams. Okay, let's write that down. So aluminum, the atomic mass unit is 26.98 grams per mole. And I'll be honest with you, I could probably just write down 30 grams per mole. Yeah, that's right. You have aluminum, gold, and sodium. That's pretty cool. You should write your name like that one day. Like have it inside of the chemistry things. It'd be cool. All right, anyway. Aluminum is 26.98 grams per mole, and I have 10 grams of this stuff. So what I'm going to do is I'm going to convert this to atoms. And remember, you guys remember this conversion table thing that we made, right? Now you folks are like, oh, now I understand why why he made it so hard on us, because you have to use it later on. If I have 10 grams of aluminum and I want to convert it to exactly how many atoms I'm dealing with, I would put the 26.98 grams on the bottom, 1 mole of aluminum on top. Does that make sense? Do you understand why I put the 26.98 grams on the bottom instead of on the top? Yes, exactly, Bradley. To cancel out this grams over here, I want to cancel out that one. So this tells me exactly how many moles of this stuff, which looks to me at about maybe a little bit less than half of a mole. But what I asked you is how many molecules of this stuff. So I know that 1 mole of anything is equal to 6.022 times 10 to the 23rd power atoms of aluminum. Now I have to deal with all of these numbers. So I just multiply it through and figure it out. Someone do this for me in their calculator. What is 10 divided by 26.98 times 6.022? Let's just deal with the numbers first. I don't have a calculator on me. You're going to have to do it. Come on. A little quicker. There we go. 2.23. All right. I'll hang with that. 2.23 times 10 to the 23rd power atoms. So I have 2.23 times 10 to the 23rd atoms. Yeah. And obviously, it would be a lot of atoms because we're talking about 10 grams worth of this stuff. Cameron, how come? Why is this one not 10 to the negative 23rd? That's a good question. Because I dealt with the numbers, the 10, the 6.022, and the 26.98. When I'm multiplying and dividing scientific notation, I like dealing with just the numbers first. Okay? And I got the 2.23. You understand that part, right? And now this times 10 to the 23rd, look where it is. It's in the numerator, so I'm multiplying by times 10 to the 23rd power. So I don't have to mess with it. It's already times 10 to the positive 23rd. If I looked at it and it's had a times 10 to the 23rd power in the denominator, then I would make it times 10 to the negative 23rd power. Does that make sense? Okay. I'm glad you asked. Now, technically, class is finished, and I really want to get past this idea of a mole and move on to stoichiometry. I'll be honest with you, I don't feel like I can lecture through this whole chapter in 2 days, so I might, spend some more time on this. I know you folks have to go. Let me just take a look as to what's coming up and how far I got. Calculating numbers of atoms. Calculating number of molar mass. All right, so it'd be important for me to get to molar mass on Wednesday. And then what is this? Is this, balancing equations? Yeah, that's important. Okay, all right. On Wednesday, yeah, you guys get out of here. Go to Spanish. But on Wednesday, expect to hang with me for pretty much the whole time. All right? Yeah, no, I'll end class. You guys can go to Spanish. But expect to spend the whole time with me, even though I usually end early on Wednesdays that we don't have lab. Expect to spend the whole time with me. We're just going to go through this painful, a lot of this stuff. Because a lot of this is math, and I know a lot of you folks want help on this. All right. Also, I'm inviting you folks to tutoring tomorrow. Please come. Okay, bye.